Now, I spent a lot of time doing mostly programming in C. There are some good things about the C language. It's simple. It works really well. It builds small executables. It's very, very close to the hardware. And you're seeing a lot of resurgence in C programming these days because of the fact that it's close to the hardware and works well on very small systems. And I found out that my light bulbs that I can control with my phone here, that they actually have a Linux operating system. I've actually logged into my light bulbs, yes. And it's written in C. Python is written in C. Windows is written in C. A lot of things, major pieces of software are written in C. But we're seeing this new language. It's about 10 years old now, Go, because it has some properties. So I've talked a little bit about the fact that a multiprocessor environment is very good for this. Ethereum is written in Go, as are a number of other things that are blockchain related. It's a big Go application. So, what's special? The first thing that is special is it's fast to compile. And that turns out to be a huge advantage for development. You know, you're working on something in Java and you see that there's a spelling error in a comment. By golly, you aren't going to compile it and change the spelling error. You're just going to ignore it because it's like, well, there goes a half an hour if I wanted, tweak something completely meaningless that I don't have to even test, but there goes a half an hour. So if you compiled the same size program in Go, you might be looking at 2 to 3 seconds if it's a fresh compile, or probably less than half a second if you've previously compiled it, if it doesn't have to do as much. And Go is really good. It's a modern compiler. It does not work the way they talk about in compiler construction. It keeps a cache of all the things you've compiled, and it only recompiles the piece that you need to recompile to get the answers you need. And then it links it and it's done. So realistically, you can compile a 250,000 line program, change one line and recompile it, and you're still in here at this kind of time frame. That makes a tremendous amount of difference. It'll make a tremendous amount of difference in how happy you are using the language long term. You're not sitting around there waiting with your mind going, yes, I wonder if I did this right or I did this wrong. You are, okay, compile it. Oh, there we go. That's what I do next. You stay in the flow. The second thing is its garbage collector. The garbage collector is incremental in Go, and it is incremental on each of the Go routines in the language. It also does dynamic memory allocation for the Go routine. So it's not like a thread in Python where you have to say, I want this big a stack, and if I run over this, my thread dies, or in C code, or in a lot of other things, or I have to build a stack big enough for my worst case. When a Go routine runs, it just runs, and if it runs out of stack space, it doubles it. But it manages to copy that Go routine data to a new location and continue running it, and you never see it. So Go routines start out with 2K, and they'll grow as they need. And if after a while and it garbage collects the data on it, it finds out that you don't need 2K, it'll shrink too. So they can grow and shrink dynamically. But that's not the garbage piece that I'm talking about. The garbage piece that is important is that the garbage collector is incremental and can run continuously. So if you have a system out here, let's say you've got a computer, and it's got a whole bunch of different CPUs in it. And one of those CPUs it will take and dedicate to garbage collection. So this guy is just going to run garbage collecting the whole time. That's all it's going to do. But all those other CPUs, can sit there and actually do useful work. And internal to the language, it has its own scheduler. And if it finds out that one is not enough to do the garbage collection, it'll allocate another CPU. But in a 96 CPU system, and I've worked on some, I have never seen more than one of them running. And it's continuously running, just garbage collecting, just going around through the Go routines. You're running 500,000 Go routines, and It's just chunking down through them, garbage collecting each one. And at the moment when it garbage collects a single go routine that isn't that big, it does it in under 100 milliseconds, and nobody ever sees that this thing didn't run for 100 milliseconds. Which means that practically you can allocate about 80% of a machine to run and go. Now, Java implemented a year and a half ago, about a year ago actually, a new garbage collector that took its allocation percentage from about 20% up to about 31%. So that's what you can do in Java in terms of allocating the machine. If you allocate above these numbers, and these are right at the peak where you're seriously in trouble if it runs over this. If it's using more than that much of the machine, when it goes to garbage collect, that machine is just going to check out for a couple of minutes. The whole computer. Okay? So you're running this little interactive application, suddenly it just goes, oops, it's gone. It's not responding anymore. What happened? Well, it's garbage collecting. So the big thing why you would go from something like that to something like this is the garbage collector. And I know it's hard to get excited about a garbage collector. It's like, Well, it turns out that the advent of object-oriented programming and dynamic memory allocation, the big thing that made computer programmers more productive when they used these languages wasn't the object-oriented stuff. Object-oriented can be good, it can be bad, depends on how you use it. It was that it had a garbage collector. And garbage collectors just about double the productivity of programmers. And I have good experience in C doing this. I worked for a company and they spent $45,000 for a single seat of a thing called Purify to go and find all the garbage in the code. And there's just one engineer that was assigned to it because it was an expensive piece of software. And his job was to find errors in our C code where we leaked memory. And what I didn't tell this nice guy, Rich Veet, is that to prevent leakage in my code, I had already implemented a double-entry bookkeeping system on malloc. So I had been through this multiple times with lots of tests for weeks with my own customized version of malloc hunting down the same problem. Because getting things so they don't leak is really, really hard. Not a little bit. I mean, talking incredibly hard in C. So, yeah, a garbage collector. That's a big deal. You don't have to use tools like that. It just works. In fact, news from the field in the land of Go programming is that if your program doesn't leak a little bit, the garbage collector actually runs slower than when it does leak a little bit. So you would actually like to give it something to do so that it can find some stuff and collect them over time. So those are kind of the high-level things. Now, another thing that it has is maps. And a map is a relationship between a key and a value. And it's implemented as a hash. Okay? For any size in Go. It's a hash lookup table. If it's small enough, it actually does a binary search instead of a hash. But it detects when it should switch between the two. So this is a fast way. So I can say that I want to declare some variable m1 to be equal to make a map. And this is the type from a string to an integer. And then I can say m1 sub key, let's say Tim, equals 3. And later I can say, I can pull this key out. So I can build this table that's indexed by this. Now the indexing type in here can be any serializable data type in the language. And believe me, that constitutes a lot of things. You can't take a communication channel and stick it in there. But lots of stuff, you can take the address and you can do a map on addresses of code. And it's very happy to not just do that, but even when it comes back and moves your code, it still keeps the map accurate. It updates the pointers. So it knows about the pointers. And knowing about the pointers and where they are in your code and how they're used is built into the language, and they're type-safe pointers. So you can get a null pointer reference like C, but it's hard. And it's usually fairly obvious, like you failed to allocate the variable the very first time. There are very few null pointer problems, and there are no typing problems because pointers are type-safe. Every time you use one, it checks the type. It knows the type at compile time, it checks it at runtime. So they are type-safe pointers. So maps. What is the other thing? Okay. Arrays and slices. Now, Go has arrays, and for people that have programmed in other languages, you use arrays pretty commonly. Arrays are rarely used in Go. Here's how you declare an array. We have some sort of a var x, and you put in a constant here, 4 of int. That's an integer array. It's 4 long, it's allocated on the stack, or dynamically depending on how you use it. Now, you can have a slice, let's say y, and you don't tell it how big it is, of int. And a slice in Go is composed of a pointer to the data. Okay, so we've got a pointer here, and 2 numbers, the current max and the allocated. So the pointer points at the beginning. The current max says how many of them have I used, and what is the allocated is how many of them are available. And when you use things and you append to a slice, Go just goes out and allocates more space if there isn't enough. And you can do other things, like you can say my slice is big and I'd really like to chop it off here and get rid of some. When it copies a slice, okay, it gives you a new slice that's just a pointer to the same thing. Okay, and if you then go in and update one of the values, it copies on write to duplicate the values of the slice. So there are lots of things going on underneath the covers with slices that make them useful and quick and fun. And generally speaking, when we work with strings, we're not working with the actual string, we're working with a slice of runes. And that slice of runes, okay, is what is manipulatable, whereas the string itself is not. Okay? Which is another thing that goes on inside this language. Now, I mentioned one thing. I said that var x gets allocated on the stack or dynamically based on how you use it. And that's an important thing to know. In Go, I can have some function, some little function, and I can say, in this function, I missed the return statement here. We'll do returns an int, a slice of int, something like that. Let's just rewrite that line. I can have a function, xx, that returns a pointer to an int. Let's do it that way. And inside here, I can say var x is an int, and I can say return and x. Now, for you C programmers out there, or C++ programmers, most of you have had C++, you could create a local variable inside there and you return a pointer to something on the stack. This is called kaboom time. Things are going to go bad. Go is not like that. Go looks at this and says, I see that this got returned outside the scope of the function, and therefore that is allocated on the dynamic heap automatically and not locally to this function. And it does flow analysis to figure that out for you. So you can have things that you just declare them, you just return them, you don't worry about the allocation. It just happens. It's just kind of fun and easy, and it just happens. And that's, where it goes. All right, these are kind of the things, okay, with it allocating and using stuff. Let's take a look at Go routines.